Hi everybody, welcome to lecture 16 of Electrical Engineering 331. In this lecture we will begin discussing one of the truly major topics in this course, and that is Laplace transforms. We will now, with this lecture, we will move into chapter 3, as you can see here. The Laplace transform of a time domain signal x of t is usually designated by capital X of s, and it is defined as being the integral from 0 minus, which means the time just before t equals 0, but it's the integral from 0 minus to infinity of x of t e to the minus st dt, where s is a complex variable. The real part is equal to sigma, and the imaginary part is equal to omega. So let's look at a few examples of calculating the Laplace transform of some signals. So we know that the delta function, we have seen that it is a very useful function that pops up a lot in this course. So let's look at the Laplace transform of the delta function. Well, this is the easiest function of which you can take the Laplace transform, because when we plug the delta of t in for x of t into this formula, then we have integral 0 minus to infinity of delta of t e to the minus st dt. And remember that as long as the region of integration contains t equals 0, then, or let's say, as long as the region of integration contains that point where the argument of the delta function goes to 0, which in this case is t equals 0, then the value of the integral is just the rest of the integrand evaluated at t equals 0. And of course, the rest of the integrand is just e to the minus st, and when we evaluate that at t equals 0, we get e to the 0, which is 1. So the Laplace transform of delta of t is simply equal to 1, and it really can't get much simpler than that. Okay, what about the Laplace transform of u of t? Well, again, plugging it into the formula for the Laplace transform, we will get this. Now remember that u of t is equal to 0 for t less than 0, and it's equal to 1 for t greater than 0. So we can take that little minus sign off the 0 here and make the lower limit of the integral 0. And we can take advantage of the fact that u of t is equal to 1 over all positive values of t. So that just basically disappears, and we're left with the integral from 0 to infinity of e to the minus st dt. And so we almost have the form e to the u du. We need a negative s on the inside and a negative 1 over s on the outside. And when we do that, then we'll have minus 1 over s e to the minus st from 0 to infinity. Now, this is the only time that I'm going to be extremely careful about substituting in these limits, and you'll see what I mean right now. So when we plug in, we have this minus 1 over s, so just bring it over here, and when we plug in infinity as the top limit, and really, you know, infinity is not a number, it's more like an idea. You approach infinity. You never really reach infinity, you approach it. But so whenever you see infinity in a problem, you really don't think of that as really a number so much as just the idea that you're going toward infinity. But anyway, so I'm going to write this though as e to the minus s times infinity here when we evaluate this at the upper limit, and then at the lower limit we will have minus e to the minus s times 0, but e to the minus s times 0 is just e to the 0, which is 1. So we have this. Now, as I said a moment ago, when we first, up here, when we first defined the Laplace transform, s is equal to sigma plus j omega. So let's substitute that in for s here. And so when we do, this first term, when we plug in s is equal to sigma plus j omega, then that can be broken up into two terms, e to the minus sigma times infinity times e to the minus j omega times infinity. And then the minus 1 over s comes down, and minus 1 comes down here. Now, our reasoning at this point is that e to the minus j omega times infinity, that just has a magnitude of 1. Regardless of what omega is, this is just a number on the unit circle in the complex plane, so it always has a magnitude of 1. But this term e to the minus sigma times infinity, if as long as sigma is positive, then this will be e to the negative infinity, which is 0. So as long as we assume that sigma is positive, then this first term will be 0, and we have minus 1 over s times minus 1, which is 1 over s. But again, that's only true if sigma is positive. So we conclude here that the Laplace transform of the unit step function u of t is equal to 1 over s, but with the restriction that sigma must be greater than 0. Now, sigma greater than 0 is referred to as the region of convergence for this Laplace transform, or the ROC. And this is described just a little bit in section 3.1-2 in your textbook. And your textbook takes the attitude that this is really not a topic that needs to be discussed any further. So for the remaining examples of Laplace transforms, I will not be worrying about the region of convergence, and the same is true for your book, but at least you've seen it here one time and you get the idea of what we're talking about. But we won't otherwise talk about that anymore for the present. Okay, so we've looked so far at the Laplace transform of the delta function, the Laplace transform of u of t. Both of those, of course, are singularity functions. Here's the Laplace transform of delta t. Here's the Laplace transform of u of t. So why don't we think about another singularity function, r of t? Okay, the Laplace transform of r of t, again, plugging it into the definition for Laplace transform, we get this. And keeping in mind that r of t is equal to t for t greater than or equal to 0, and is equal to 0 whenever t is less than 0, that tells us then that we can plug in t here and change the lower limit from 0 minus to 0. And then e to the minus st we just bring over. Maybe I should make one quick remark. You might be wondering about this 0 minus here. You might think, well, can we not always substitute 0 instead of 0 minus? And the answer is no. The 0 minus is, in some problems, very important. Let's come back up here to the first one. If the lower limit here had been 0 instead of 0 minus, then this would be sort of cutting the delta function in two, because you remember that the delta function is located right at 0. And so that's why we want to, while the definition, the 0 minus in the definition is important. So remember that. Admittedly, if the function you are considering is finite at t equals 0, then this won't make a difference. But if it's infinite at t equals 0, like the delta function, then it definitely does make a difference. So let's adopt the practice of always keeping that 0 minus there, and that way you won't get in any trouble. Okay, so anyway, as we've argued then, in this case, this becomes, the lower limit becomes 0, and we have a t here where we had r of t. And so now that you have this integral, you can see that this is an integral where you would want to use integration by parts. So I would let u equal t, and the rest of this I would let be equal to dv. And so du is dt, and then minus 1 over s e to the minus st is equal to v. And then you know how the usual integration by parts formula goes. It says the integral of interest is equal to uv minus the integral of v du. And so that's what we have here. This is, here's u is the t, so that's u, and v is minus 1 over s e to the minus st, so you can see here's uv, and then minus the integral of v du, minus the minus gives us plus 1 over s, and the integral of v, here's your v, and du is just dt. Okay, so the way that we now finish this discussion is at the upper limit. Don't let this fool you here. At the upper limit, admittedly, t, as we go to infinity, t goes to infinity, so that's very big, but e to the minus s times infinity is going to 0 much more quickly than this is going to infinity. So at the upper limit, we have 0, and then at the lower limit, because t is equal to 0 at the lower limit, we also have 0 at the lower limit. So this term is just 0. And then over here, we have a 1 over s, and then we need to get this integral in the form e to the u du, we need a negative s on the inside and a negative 1 over s on the outside. And here's e to the minus st from 0 to infinity. And so we get this 0, of course, can be ignored. 1 over s times minus 1 over s is minus 1 over s squared. At the upper limit, this is e to the negative infinity, which is 0, minus the value at the lower limit, which is e to the 0, which is 1. So we have negative 1 over s squared times 0 minus 1, or 1 over s squared. So the Laplace transform of r of t is 1 over s squared. Now, let me point out something to you. Let's review what we've said so far and see if you begin to see a pattern. The Laplace transform of delta of t is equal to 1. The Laplace transform of u of t, which is the integral of delta of t, is 1 over s. The Laplace transform of r of t, which is the integral of u of t, is 1 over s squared. So it's looking like the Laplace transform of the integral of a function is 1 over s times the Laplace transform of that function, and that is indeed true. This is called the time integral property of the Laplace transform, and to be very specific here, it says the Laplace transform of the integral from 0 minus to t of x of tau d tau is 1 over s times the Laplace transform of x itself, x of s. Now, just to make sure that's perfectly clear, then saying again in detail what I already said and sort of sketched above, the Laplace transform of delta of t is 1. We've seen that. The Laplace transform of u of t above, we found out that that was equal to 1 over s, and we found that out by direct integration using the formula. But we could also arrive at that same result using this time integral property, as I show here, because the Laplace transform of u of t is the same as the Laplace transform of the integral from 0 minus to t of delta of tau d tau, which, according to this time integral property, is 1 over s times the Laplace transform of delta of t itself, which is 1 over s times 1, which is 1 over s. So here we get the same result, that the Laplace transform of u of t is 1 over s, but in an entirely different way from the way we used above. And similarly, for the Laplace transform of r of t, we found out above that that is equal to 1 over s squared by doing the direct integration of the formula. But if we use the time integral property, we could go in this way. The Laplace transform of r of t is equal to the Laplace transform of the integral from 0 minus to t of u of tau d tau. So that means that this Laplace transform should be 1 over s times the Laplace transform of u of t, which is 1 over s times 1 over s, or 1 over s squared. So you can see here, again, we're getting the same result, but in a different way. So that gives us, we have now three Laplace transforms. We have the Laplace transform of delta of t, the Laplace transform of u of t, the Laplace transform of r of t, and now we have an important property, the time integral property. And before I go any further, let me say that this is the idea with Laplace transforms. You build up a table of knowledge. These things were referred to, these first three things that we found are referred to as Laplace transform pairs. Why do we call it a pair? Because each one really consists of two things. It consists of a time domain function and its Laplace transform. So here the pair is delta of t in 1. Here the pair is u of t in 1 over s. Here the pair is r of t in 1 over s squared. And on the other hand, here we have a property. So usually, and this is the case in your book, you have tables of Laplace transform pairs and tables of Laplace transform properties and theorems. And both of these are important. In your book, these are tables 3-1 and 3-2. And by using these tables, showing you some fundamental pairs and theorems and properties, the idea is that then by using that information, you can find the Laplace transform of many other functions. And we will see some of that later on in this lecture. Okay, so far we have three pairs and one property. And so let's look at something else. Here's another example for you. The Laplace transform of e to the minus at u of t is certainly of interest. We've seen many times that we've looked at signals that look like that. And so plugging that into the formula for the Laplace transform gives us this. And we can group together the e to the minus at and e to the minus st as e to the minus quantity s plus at. And as usual, u of t is equal to 1 over positive values of t and 0 over negative values of t. So we can change this 0 minus to 0 and then get rid of the u of t. And now this almost has the form e to the u du, but we need a minus s plus a on the inside and a minus 1 over s plus a on the outside. And so we would have this, and then as usual at the upper limit, then we'll get 0. At the lower limit we get 1, so we have minus 1 over s plus a times the quantity 0 minus 1, which is 1 over s plus a. So here is a fourth Laplace transform pair. Here the pair is e to the minus at u of t in the time domain, or 1 over s plus a in the s domain, or Laplace transform domain. And again, this is a result that is consistent with one of our formulas. In this case, it's called the frequency shift property, which is says that the Laplace transform of e to the minus at times any time domain function will simply be the Laplace transform of that time domain function evaluated at s plus a. And so to see that, to let me explain now how that shift property could give you this same result, I think it's pretty clear, but just to make sure, okay, the Laplace transform of e to the minus at u of t is equal to 1 over s plus a. We found that up here by doing direct integration. But how could we do it? How could we find that out using the frequency shift property? Well, remember that the Laplace transform of u of t, which we could call u of s, is equal to 1 over s. We found that earlier in this lecture. So according to the frequency shift property, the Laplace transform of e to the minus at times u of t is u of s plus a. That's just this property right here. But then since u of s is 1 over s, then u of s plus a is 1 over s plus a. So there we have found the Laplace transform of the e to the minus at u of t using the frequency shift property rather than by using the direct integration of the formula. So now we have 4 pairs and we have 2 properties. Now let's look at still another pair and another property, okay? So if we look at the Laplace transform of u of t minus capital T, where capital T is greater than or equal to 0, let's see what that will do for us. Well, that will be the integral from 0 minus to infinity. This is just plugging directly into the formula for the Laplace transform. And now we know that u of t minus capital T will be equal to 1 for little t greater than capital T, and 0 for little t less than capital T. So we can change the lower limit on the integral to capital T, get rid of the u of t minus capital T, and we have e to the minus st dt. And we've integrated this function before, it's just that we have different limits this time. And so we get minus 1 over s times at the upper limit we get 0. But now at the lower limit, since we no longer have 0, but instead we have capital T, at the lower limit now we don't no longer get 1. Instead we get e to the minus s times capital T. And so we conclude then that the Laplace transform of u of little t minus capital T is equal to e to the minus st over s. And again, that's assuming that capital T is greater than or equal to 0. Now once again, okay, so here is a 5th Laplace transform pair for us. And once again, this is still another result that could have been derived using one of our properties. Now I want to say something here. The property in question this time is called the time shift property, and this is the way that I would recommend that you think about the time shift property. The Laplace transform of x of t minus capital T is equal to e to the minus st times capital X of s. And that's good for t greater than or equal to 0, and where x is a function that is equal to 0 for t less than 0 minus. Now, I want to warn you that this is not the same form that you will see in your book. In your book, in table 3-1, you will see the time shift property looks a little different. And if you feel more comfortable working with the formula that's in the book, by all means go ahead. But I think that if you do that, you will find it's a little bit cumbersome. That formula is a little bit more awkward to use, and I think that, you know, in my opinion, you ought to use the time shift property in this form. And just for a reference, you know, in case it makes you feel a little uneasy using a form that's a little bit different from what's in your book, here I have put a reference for you, and you can find in that at this website, which is affiliated with MIT, you will find the time shift property written in this form. So that's what we will use for this course because I think it's easier. Okay. So now let's move on. Remember that what we're doing now is we came up with this Laplace transform pair by direct integration of the Laplace transform formula, the definition. But I'm showing you, now I'm going to show you how we could come up with that same result using this time shift property. So the way it would go is this. The Laplace transform of u of t minus capital T, where again capital T is greater than or equal to 0, is equal to e to the minus st over s from above. Okay, that was the result we came up with here. But now the way that we could get it using the time shift property is the following. we say the Laplace transform of u of t minus capital T could be thought of as the Laplace transform of x of t minus t, where x of t is equal to u of t. But according to this time shift property, then, that will be e to the minus st times x of s, where again x of t is u of t. So x of t is the Laplace transform of u of t, which is 1 over s. And so what do we end up with? E to the minus st over s, which is exactly the result we obtained up above using the Laplace transform formula. But here we obtained it in a different way using the time shift property. So that's another transform pair for us and still another property for us. Okay. So now that we've learned a few Laplace transform pairs and a few properties, we can do some problems. And as I mentioned before, if you go in your textbook and look at tables 3-1 and 3-2, you'll find more properties and Laplace transform pairs. And once again, the strategy for very many Laplace transform problems is to try to manipulate the data you have and put it into a form that matches something in the table, and then use the table to finish the problem. So now we will look at 2 problems that will help to prepare you for the test on this lecture. So the first one I want to look at is problem 3.1d. It says find the Laplace transform of x sub 4 of t, and x sub 4 of t is shown here in this graph. They refer to it as the mesa. So if you look at x sub 4 of t, this is a good review of some previous work we did in this course where we want to express functions in terms of singularity functions. So you see here clearly a ramp function, and notice that it goes up a distance 4 and a vertical distance 4 and a horizontal distance 2, so the slope is 2. So the first part of this is 2r of t. Then at t equals 2 it flattens out, and we know that to make that happen we need to subtract 2r of t minus 2. That will make this flatten out and stay like this, but then at t equals 6 we want it to go down. And let's see, how much is it going down? Well, it's going down 2 units from 4 to 2. It goes down 2 units in a horizontal distance of 1, so this slope is negative 2. And that's why we have negative 2r of t minus 6. That will give us this, and then we want that to flatten out, so we add plus 2r of t minus 7. That will make it flatten out starting at t equals 7. So now that we have the function written like this in terms of singularity functions, well, it's really pretty simple to then find the Laplace transform of that. We know from above the Laplace transform of r of t is 1 over s squared, so the Laplace transform of this first term is 2 over s squared, and then we can get the Laplace transform of all the remaining terms using the time shift property. So we have minus 2e to the minus 2s over s squared, minus 2e to the minus 6s over s squared, and plus 2e to the minus 7s over s squared, repeatedly using the time shift property. So that's how we would do problem 3.1d. And now for one more example. Problem 3.6b says find the Laplace transform of x of t where x, I'm sorry, this should be x2 of t here. Let me see. Okay, I had that right there. I said x4 of t, and this is x4 of t. But on this one, I should have said x2 of t because this is x2 of t. So let me stop for just a moment and correct that little typo. Okay, so now the 2 is there. So find the Laplace transform of x2 of t, where x2 of t is equal to 5 times the quantity t minus s multiplied by u of t minus 3. Now, this is a little tricky here because we have t minus 6 here and u of t minus 3 here. So let me show you a strategy for working problems like this. I am going to call this function over here on the right-hand side x of t minus 3. Now, how did I choose x of t minus 3? Well, it's because the argument of the u is t minus 3. See, what I'm going to do is I'm going to define x of t minus 3 to be equal to this, and then I'm going to shift t by 3 units, so it becomes u of t. Why do I want to do that? Because if you look in the tables, many of the functions in the two tables, 3-1 and 3-2, are multiplied by u of t. So if I can shift this by 3 units, there will be a pretty good chance that I can find something like it in the table. So, like I say, if I define this to be x of t minus 3, then when I shift this by 3 units to get x of t, then this will also get shifted by 3 units to give u of t. But the only way that that works is if I have this argument for the x function the same as the argument for the u function. Okay, so I'm going to say that this stuff on the right, 5 times t minus 6 times u of t minus 3 is equal to x of t minus 3. And now, everywhere in that equation, I'm going to replace t by t plus 3. So then I'll have x of t plus 3 minus 3 will just be t. And when I replace this t by t plus 3, then I get t plus 3 minus 6. And then this will become t plus 3 minus 3. So I have 5 times 3 minus 6 will be minus 3. And t plus 3 minus 3 will be u of t. And so that means that x of t is equal to, multiplying out, we'll get 5t u of t minus 15 u of t. Now that's x of t. And remember that x2 of t is equal to this, which is the same as x of t minus 3. So x2 of t is equal to x of t minus 3, where x of t, we have found out, is equal to 5t u of t minus 15 u of t. Well, this is great because now use the time shift formula here to tell us, to determine x2 of s is equal to e to the minus 3s x of s. X of s is the Laplace transform of x, but here we have x, and so we can take this is something that matches a form in the table, so the Laplace transform of that is x of s, which is 5 over s squared for this first part, minus 15 over s for the second part. So that's x of s, and x2 of s is just that multiplied by e to the minus 3s, and so here we have our final answer. x2 of s is e to the minus 3s times 5 over s squared minus 15 over s. By the way, be careful in Laplace transforms, be careful in any problem that has a 5 in it, because 5s can look very similar to s's. Okay, but that's how we would do a problem like this, using, getting, as I said, getting our function into a good form that will allow us to then use the properties and the tables, the pairs and the properties that are in the tables to get our final result. And so that is the last example for lecture 16, and I hope that will help prepare you for test 16. And so that concludes lecture 16, and good luck.